So hi everyone. My name is Navneet and I'm currently in EE21 and I'll be giving a seminar on feedback control systems. Exactly what is their concept and how they have evolved. So what exactly are feedback systems? So feedback systems are basically systems which use the output to modify the input to achieve some desired result or to maintain some particular state. That's simple. You use the output to modify the input. And this feedback control is seen everywhere. It is seen mechanically, electrically, and even biologically. Like our body itself, it maintains our body temperature using feedback mechanism. If our body temperature goes too high, there is a vasodilation or vasoconstriction happens. That's that the temperature reduces. And the flowchart here represents what I just said. So negative feedback loops are seen everywhere and they're basically used to modify some state variable using the output. A device using a feedback system is also called a closed loop control system because, again, the output is fed back into the input. This is the basic flowchart of how a feedback system works. You give the input, you find the error using the feedback signal. This error signal is appropriately analyzed using a controller, and then it is sent to an actuator which gives the output and a plant which gives the output. And this is again fed back into the input using feedback. Now, where can you see these feedback control? Where can you see feedback naturally and man-made? So a really interesting point I'd like to bring up is that our evolution, human evolution, is the most perfect example of feedback. Evolution over a long time is only due to feedback over long periods of time, and it's responsible for evolution. So if a species does well, that is basically fed back in, and it says, okay, this species is more suitable, and more of the species grows. So Darwin actually proposed that evolution is actually primarily due to feedback systems. A mechanical example I can show you here is actually what we use in our everyday life to flush in our toilets. So what happens is if the water level increases over a certain limit, this floater closes the valve and basically the valve shuts and the water flow is stopped. And this is again a beautiful example where the height is the state variable and it is fed back in as an input as using the floater. Another typical example are automobiles, and this is feedback we generally start feedback with, and we learn how feedback works. It's quite simple. The car measures the difference between the speed we want to go and the actual speed, and it varies the fuel rate accordingly to increase or decrease the speed. Quite simple. So I've told you what feedback is and a few applications, and these can be seen. It's prevalent everywhere. You can see it in aerospace, nuclear reactors especially, and of course your electronics, which we'll focus on with your op-amp circuits and your oscillators. This is a picture of an op-amp. Now let's come to the beginning. Let's go to the early feedback systems. How exactly the feedback systems evolved from scratch. So the first few feedback systems were definitely mechanical devices. There was no electronics back then, but they still embody the idea of feedback. So what they embodied, so a beautiful example is this water clock to keep track of time. So keeping track of time became more and more prevalent around the 1500s and thereon. And they used these water clocks, which basically kept track of time using the water level, as like we saw in the flush. As the water level increases, this dial turns by a certain amount of degrees. And it's as simple as that. And this water supply is controlled using this increase in the water level. So it dictates how much water should be supplied and accordingly how much the dial turns. Another great example are the steam engine, and probably the first major mechanical example of feedback systems. And it was actually probably the beginning of like the crazy growth of feedback systems in the 19th and 20th century, especially. So they were used in steam engines to regulate the speed and power output of the engine. This was done by regulating the flow of steam into the engine. Again, quite simple, just like our lever and valve. It regulates how much uh, input we give based on the output. This is a nice picture on this, showing the governor and throttle valve. Now let's come to the evolution of classical feedback system. So probably the evolution of feedback systems was divided between the classical feedback systems and the modern feedback systems. So let's go over how the classical feedback systems evolved. And this all started, like with most inventions, the Industrial Revolution. So during the Industrial Revolution, V.B. Airy, he developed a feedback device for pointing a telescope, and it was similar to it's probably the initiation of how a gyroscope was built. And what he did was he saw that when a feedback loop was not designed perfectly, when there was a few oscillations, when there was ringing, depending on the Q factor, there were a lot of oscillations in the system and ringing, and that made the system very unstable, and we wouldn't want that in our design. So he analyzed this and came up with the differential equations governing these feedback systems, and he used that to analyze instability in these closed loop systems. So this was the start of analysis of feedback loops, scientific analysis of feedback loops. Then came the well-renowned J.C. Maxwell. He analyzed the stability of Watt's flyball governor, and he concluded that a system will be stable if the roots of the characteristic equation have negative real parts. So using that differential equation, when you find the roots of that equation, if that equation has negative real part, if the roots have the negative real parts, then that system is stable. And we still use this today in a very surface level analysis of feedback system. And this is a great contribution to feedback system. And thereby Maxwell established the initial control theory, or the initial theory of control system. A.B. Stodola also came up with that time constant. He came up with a term called time constant, which basically we use a lot in our feedback systems, especially when capacitors and inductors are in. And these are basically the starting point to the growth of feedback systems. Now comes the innovation at Bell Labs. Bell Labs is really well renowned and probably one of the hubs of greatest innovations in the 20th century. And especially due to the world wars, there was great motivation for innovation, and it's especially in the communication field to win the war. And here, the mathematical analysis of control systems was carried out in the frequency domain. So Maxwell and Airy, all of them had done a precursor in control system, basically a very surface level analysis using time domain differential equation. Now the Bell guys, they came up with very intuitive analysis using frequency domain analysis, especially using techniques developed by Laplace, Fourier, and Cauchy, which we all are very familiar with. And between 1920 and 1930s, this analysis using frequency domain saw a huge boom, and its applications were unnumbered. And this showed a clear shift from the time domain to frequency domain analysis. And this is what the classical theory is based on. The classical theory of feedback analysis is based on frequency domain analysis rather than time domain analysis. So classical is analogous to frequency domain analysis. And three men actually in Bell Labs took this analysis, this frequency domain analysis, to another level. By the way, Bell Labs is a company in the United States, and this was during the World War. It was probably one of the biggest companies in the world at the time, and they worked on a lot of different things. And it actually came from the telephone, the invention of telephone by Graham Bell, hence the name Bell. Now we come to Harold Stephen Black, and he was again the probably one of the fathers of the classical era of feedback systems. So Mr. Harold Black worked in Bell Labs in the mass communications division. And what he was majorly known for was the concept of negative feedback, which we still use and learn today. He wanted to reduce distortion in his amplifiers, which he was using in the telephone line, which Bell was working on. And he realized that by feeding back the output to the input, we can minimize distortion and get a clean output. And that thereby came the analysis of negative feedback. He also came up with the accurate design of fire control systems in World War II, and again was a major contributor to to America's success. And of course, he formed the basis of operational amplifiers, which are completely based on negative feedback, and we still use today. Next comes probably the most important figure, and his techniques are still taught in the classes today, and he is Harry Nyquist. So he was one of the stars of the Bell Labs team, and he came up with a lot of different things, especially his regeneration theory, which was used for the design of stable amplifiers, which Harold Stephen Black was working on. And he majorly came up with his Nyquist stability criterion based on the polar plot of a complex function. So this is the Nyquist plot here. And this plot is really beautiful and really easy to understand. To understand frequency domain analysis, you don't need any complicated time domain differential equations, but just by looking at a diagram, you can come with so many conclusions. So here what is represented is that the gain and the angle or the phase is represented parametrically, and it is plotted against the frequency of the system. So the gain is the radial coordinate here, and the phase is the angular coordinate. And the number of times subtracted by 1 represents the difference between the number of poles and zeros. And this can be used to ascertain stability of a system and determine how a system would behave. Because we need our poles and zeros, and then after that, we can analyze a system beautifully in the frequency domain. So again, yeah, he came up with the term called loop gain, which is basically the feedback factor into the gain of the amplifier. And this again simplified the stability analysis a lot. And this analysis is the most comprehensive one in the frequency domain, even better than Bode's analysis, which we will cover later. And it can work when the system is unstable too. Most importantly, this was also a precursor to time domain analysis, which was extended to multiple input, multiple output systems, and nonlinear systems, Lyapunov's method, which will be very prevalent in the 1960s. So even though here he uses only LTI systems or linear time invariant systems, it can be extended to multiple input, multiple output systems and nonlinear systems, which is really, really important. So this man was truly revolutionary in the classical domain analysis. Now we come to Hendrik Wade Bode. I mean, a lot of us are familiar with his Bode plots and his frequency domain analysis. And let me tell you a bit about him. So he is also regarded as the father of information theory. He developed with these plots called Bode plots, which basically use the magnitude and phase frequency response to analyze stability and to analyze the feedback system. So these are the plots. These are these asymptomatic plots, and they can be really easy to analyze to understand if there is ringing in the system, if the system is unstable, what poles we should introduce, where we should introduce capacitors, etc. It's a really intuitive way of understanding. He also came up with the idea of phase margin. We all know if phase margin is less than 0, then that system is unstable for sure at unity gain frequency. And this concept of phase margin is so handy in designing feedback systems. And it is really important. And Hendrik Wade Bode is the one who came up with this. He also worked with automatic artillery weapons and anti-ballistic missile systems. So with his theory and knowledge of feedbacks, he helped the US in tracking systems, in weapons tracking systems, which needed accuracy in location and, of course, needed feedback systems in their gyroscopes. And once again, his Bode plots and his analysis of feedback system was the fastest and the most intuitive way we could analyze feedback system. And it's still used by students in colleges now. So after this, as I said, the scientists I mentioned, They were working on developing feedback systems. But what was their main motivator? Their main motivator were the world wars. And the world wars were truly a catalyst to develop. Because now feedback systems were literally a matter of survival. Because location tracking of their weapon systems was so important and could win wars. And that accurate location tracking could be done only using accurate feedback systems. And this led to the invention of the PID controller, the proportional integral derivative controller. And this was brought up by Minorski. And he used this three-term controller to steer ships. And I'll talk about this in the next slide. Also, the Norden bomb site, which is basically this, was a location tracking device. It basically gave information on the position, the velocity, the altitude of an aircraft, and it ensured that the weapons could be delivered to that aircraft accurately. So weapons delivery became very accurate using this Norden bomb sight. Here's a picture of that. Fire control systems, as I said, radar technology using feedback systems again became really popular and really important to win the wars. Now we come to the PIDs. So these PIDs, they basically made navigation really easy. And it's almost like an advanced gyroscope. It's a control device that was an advanced gyroscope. And it enabled engineers to design and tune complex control systems. And it was the culmination of the work of Minovsky, as I mentioned before, Harold Black as well, and he came up with the feedback control system. We've spoken about it. And most importantly, Ziegler in 1950 came up with the method of tuning PIDs and making this PID application really accurate. These PIDs are used everywhere in manufacturing, chemical processing, robotics, everywhere. It's currently being used in levitation as well to ensure stability of the pod. This is an example of a PID, and this shows the flow chart. So let's break these down one by one. So what is P here? P represents proportional, and it's quite simple, like we see in an op amp. It measures the proportional relationship between the error and the output. So a higher P or higher gain will lead to a stronger response to the change in error. When a lower gain gives a weaker response. It's as simple as that. Now this integral, what does it do? It basically integrates this error which we calculate here, input minus output, over some time, and it multiplies with some integration constant. And this helps remove any steady state errors and provides a continuous error correction. So basically, as I deviate my location, it continuously measures this error and make sure I deviate back to the actual position which I need to be at. Next comes the derivative, D. This he also realized, so Minovsky realized that the rate of change of this state variable which we're talking about is also really important. This makes sure that there is no damping effect. It also counteracts oscillations, overshooting, because it considers the rate of change of error. It doesn't change the output extremely quickly just because the input is changed. And a really interesting story is Minovsky analyzed how a ship captain steers his ship, and he came up with these three terms: proportional, integral, and derivative. He realized that the ship captain not only changed his direction based on the error the ship is on or the error in the course, but he also turns the steering based on his past judgment, which gave him the idea of the integral and derivative. This is a really interesting story. Now we come to our modern feedback system. So what are these modern feedback systems and what is the difference? So why did we come up with this modern feedback? So classical control theory was frequency domain analysis, and it was applicable only to LTI systems. Board, Nyquist, all their analysis was applicable to LTI systems, and it was applicable to only single input, single output systems. So only when there was a single input, single output system, this theory could be applicable. Non-linear systems were a big problem, and it was since the space race was coming, a lot of analysis required non-linear analysis. This classical theory had a lot of drawbacks. This led to the modern feedback system theory, which catered to multiple input, multiple output systems, your MIMOs, and your nonlinear system, which was the biggest advantage of these modern feedback systems. And the space race, especially the Cold War between the US and the USSR, required such MIMO nonlinear systems, especially in space applications. Ironically, from Maxwell, they had changed to frequencies, from time to frequency, and now this period, this modern control systems, marks a change back from frequency to time domain analysis. So how Sputnik changed the game? This is really interesting. So Sputnik was the satellite launched, the first satellite launched, and this was launched by the USSR. So Lyapunov, as I mentioned before, he extended Nyquist's theory to using time domain analysis, and he came up with nonlinear control design. And this was a major factor in the advancement in the space race for the Soviet Union and how they could launch Sputnik really quickly. Because remember, space applications require really precise measurements and extremely precise gyroscope, and only with multiple inputs with so many different variables. And Lyapunov and his nonlinear techniques and MIMO techniques could only come up with this analysis of modern control systems and could let the USSR launch Sputnik. This also motivated the USA to come to the modern control, to leave the feedback, to leave the frequency domain and come back to the time domain. And this really motivated them to really show a boom in feedback theory. And this led to the birth of optimal control, led by R. Kalman. R. Kalman, Rudolf Kalman, is really a great man who we will cover soon. So what happened in this optimal control theory? R. Kalman realized that he analyzed naturally occurring control systems and realized that what they did was they minimized some control variable, they minimized some function, and we call it here a quadratic generalized energy function or a performance index. They basically minimize this time or this quadratic energy function with all the constraints given, this multiple inputs given, and they minimize them. So he came up with control theory based on optimization, which is why it's called optimal control theory. And this again marked the birth of the modern control era and was probably the biggest advancement in control systems. It was led by the three scientists in India, especially R. Kalman. It's a really complicated feedback circuit, but it is a gist on how optimization occurs based on the output you want to reach. So Rudolf Kalman, again the father of modern control, he was an electrical engineer who graduated from MIT and Columbia. He published three groundbreaking papers. So the first was the time domain control analysis of nonlinear systems. Second was the optimal control of systems, which again use that quadratic energy function, which he minimized, called the LQR. And the third most important one was about the Kalman filter, which he was again the father of optimal filtering and estimation theory, which is so important in today, especially. So this Kalman filter is still used in radars and GPS and computer graphics. And most importantly, for the US, this filter was used in the first lunar landing. After the Kalman filter was innovated or invented, this filter was actually on the Apollo rocket, which helped provide navigational data for the first lunar landing. So the America could not go to the moon first if they did not have this Kalman filter. And this filter provided absolute optimal solutions. And he also came up with control systems with guaranteed performance. And these controls were found using complex matrix equations, which were solved in the time domain. This is an example of how the Kalman filter works. Again, shows time domain analysis using the t+1 sample, which is the output sample, to modify the input sample. Now we come to computers in control design and implementation. So what was the major problem now in this modern theory was the cumbersome matrix equations. Back then there were no computers, so everything had to be solved by hand, and the differential equations were massive and required a lot of computing power. So this was a big drawback. So how this drawback was removed was with the invention of computers, and this boom in control theory and invention of computers went hand in hand. So with the invention of the computers, the equations became more complex, more accurate answers were found, MIMO systems were used, nonlinear systems could be used, and digital control theory was born. Because now we need to feed in information using bits, and basically converting this analog time domain analysis to digital analysis or digital filtering became really important, and digital control theory was born. Even laymen or even your engineers at home could now develop control systems using applications such as MATLAB, Oracle CL, Oracle S, and we still use a lot of these programs. This is an IBM computer, the one of the first ones. So finally, I'd like to talk about the differences between classical and modern. So what exactly is the difference? The first is that, of course, the classical control theory came first, and it focused on frequency domain. It focused on transfer function based analysis, and it was applicable only to LTI systems with single input and single output. And it deals with input and output variables, a single input and single output variable. It was much more intuitive and very easy to grasp and very easy to design these feedback systems. And it was analog in nature, and lesser computing was needed. A lot of this could be done with hand, as it was very easy to grasp and intuitive. Coming to the modern control, this was, of course, developed later during the Cold War, especially. And it focuses on time domain analysis, differential equation solving, and it can be applicable to nonlinear and multiple input, multiple output systems. And it deals with state variables mainly, rather than just input and output variables. Of course, it is definitely not intuitive. It is just a very rigorous set of equations, and it is highly mathematical. And it is digital in nature. It requires a large amount of computing resources, especially to solve those matrix equations and those differential equations. Now we come to the current scenario. So what exactly is happening now? Now, right now, the theory which is used most is the robust control theory. This has a blend of the modern and classical techniques, a blend of the intuitiveness of the classical techniques and the accuracy of the modern techniques. And this is prevalent in all industries. Control systems are so important, especially with the advent of AI and feedback systems in our technology. It has become so important in your factories and in your manufacturing. It is really important. Any automation or any robotics requires control systems, and it is completely imperative for the functioning of any technological ecosystem. Especially the advent of AI has also helped come up with much more robust and faster control systems. Literally, like control systems are designing control systems. Quite nice to if you think about it. And this has also led to the field of intelligent control systems, which again uses AI, and it is still developing today and has a large scope of growth. As I said, this has also led to huge automation in all industries. So control systems literally are the most important part of automation because they decide where your output should go. The current scenario right now, the control system market is massive at 180 billion market cap, and you have your major players well known like Honeywell, Siemens, Emerson, General Electric, Mitsubishi. And as you can see in this graph or in this picture, India, China, and US are the major markets for these control systems, and this where the work of control systems is actually happening and where automation actually is happening. This picture again shows you all the different companies working on developing these intelligent control systems as well. So that's it for control systems and its evolution. I hope you understood its concept, how it exactly works, and how it has evolved from frequency domain analysis, or rather time to frequency back to time domain analysis. And I hope you enjoyed the journey from your steam engine to your artificial intelligence control systems. So thank you for listening.